action then. Okay, in practice, the world around us is in general not a deterministic one. A great example we are used to is the art of weather prediction. So since individual trajectories for weather are impossible to predict, the possibility of rain in the near future is given in the language of statistics. So we get a probability for rain, say tomorrow. And this is done this way because even very simple models exhibit chaotic behavior.
Yeah, perhaps the most famous example of a chaotic dynamical system was actually a very basic meteorological model known as the Lorentz system in 3 dimensions. And it already is computationally intractable because even very small errors of computation will blow up very fast. And so deterministic predictions in this system are impossible.
Exactly. So the method commonly used to produce such statistical predictions consists first in choosing a large number of initial conditions. Then we ran our simulation for the desired duration for each of the initial conditions, obtaining a collection of individual trajectories. Each of them we know is off by a significant amount. And we then take the average of all these trajectories and obtain a probability measure which is supposed to describe the statistical distribution of the true trajectory of the system. More formally, we will consider a discrete time dynamical system given by a function f from a certain domain in Euclidean space. And so given, say, a large number of initial conditions, randomly chosen, say k, we will iterate each of these conditions, obtaining a trajectory, which will give a probability measure which is supported on these points, and then we will average these trajectories and obtain these finite measures, mu kn, which we expect will converge to some limiting statistical distribution. And this is the one which is supposed to give meaningful information of the system and therefore can be used to make statistical predictions.
Yeah, let's stare at this expression for a moment because we're going to see such expressions a few more times. The expressions of this sort are known as ergodic averages. The inner sum here is a sum of delta masses over points of a long but a finite orbit, starting with the point x sub L. The orbit has length n, which we consider a large number, and the division 1 over n averages over the points of this orbit. So it just gives you a distribution of a long orbit of 1 point. And then the second average in here is the averaging over the initial points. And that's our measure mu kn.
Very good. This method is known as Monte Carlo method. It was invented by Ulam and von Neumann. And actually, the story says that Ulam was sick at the hospital and he had plenty of time, so he will play a lot of rounds of solitaire. And at some point, he wondered what would be the probability of actually winning a solitaire. So he tried to compute by hand this probability, but he quickly realized that it was too complicated. And then had the idea of using the games that he had already played to actually average them out and get an estimate of this probability. So
yeah, his next idea was to use this technique to do numerical estimates of neutron diffusion, which was a problem which was way too hard for computation, even with today's computers. And he shared this with von Neumann. And in fact, if you look at the picture of Ulam on the left, he's holding an analog computer which realizes the Monte Carlo simulation for neutron transport, which was designed by Enrico Fermi and is known as a Fermiac.
Okay, so the formal definition of this limiting statistical distribution we are talking about is the following. So they are called physical measures. And so a measure is physical if there is a positive measures of initial condition, positive measure set of initial conditions, such that if we pick a point in that set and we look at the average, at the ergodic average supported on this trajectory, this average will converge to this measure in the weak sense. So this limiting measure represents measure that we can observe physically, since it will appear with positive probability.
Yeah, and a map F in principle doesn't have to have a single physical measure. It doesn't have to have any. It could have infinitely many. There's a famous class of examples, generally known as a Newhouse phenomenon, which exhibit generically an infinite set of attractant basins. So one such class of examples are quadratic polynomial maps in dimension 2.
Very good. So we will be interested when there are physical measures, and of course we wonder whether it would be possible to compute these measures. So the definition of computable measure is the following: a measure is computable if there is a Turing machine capable of computing a sequence of finite measures, which will approach the measure we want to compute at a given rate. This is equivalent actually to what is required in practice, which is being able to compute integrals with respect to this measure. Here we have an example for the Monte Carlo method applied to the logistic map there. And we can see the histogram showing the number of points that will be in a given region in the future. And this approximates nicely the physical measure of the system, which in this case is unique. And this Monte Carlo method actually allows to show that this measure in this case is a computable measure. And well, we want to study whether the Monte Carlo method works in general. So probably the simplest place to start is to consider the whole quadratic family of the interval. And for this family, we obtain the following result. So there exists an uncountable set of parameters for which, on the one hand, there exists a unique physical measure to which Lebesgue almost every initial condition will converge. And however, at the same time, this measure is not going to be computable even relative to the parameter.
Yeah, so in a strange way, the Monte Carlo approach, as well as any other approach to trying to compute the statistics of such maps, will fail, not because there is no physical measure or because there are too many of them to average. There is, in fact, in all of these examples, there is a unique physical measure whose basin is everything. So you could start with any point in the interval as your initial point. But the problem is that the ergodic averages will probably not converge to anything meaningful in a computational practice. Okay, so let me talk about the construction a little bit. To set the stage, let's introduce a notation. Let me call omega of x with the subscript a. For a given map f sub a, this will be the set of all possible weak limits for the ergodic averages. So here's a simple fact that we're going to be using. Our map as a parabola has a single critical point 1/2. So if this point happens to be periodic, then there is a unique physical measure which is supported on the orbit of this point. And its basin is the whole interval 0, 1. So for almost every x in 0, 1, the set omega a of x is just the average of delta masses on the finite orbit of point 5.
So of course, a computable measure in this case.
Yes. So now we want to start with a very specific parameter value. If I use the notation g sub a for the third iterative f, there exists a parameter value such that the second iterate of 0.5 under G is fixed. So look at this picture. The black graph is the original parabola, F. The blue graph is the graph of the third iterate. This point is a point where both the original, this point is the point where the blue graph intersects with the diagonal, so it's fixed under the third iterate. And then if you look at the orbit of the critical point, 0.1/2, well, it first goes to this point on the left, and then the second iterate brings it to this point on the right, which is fixed. Here is
yeah.
Oh, yeah.
Yeah. So it's a interesting remark that these maps are sometimes called Uland von Neumann maps. And these are exactly the maps that they use as pseudo-random generations for their calculations.
So I would like to zoom into the orbit of the critical point in this case, just to show you the same exact picture. So here is a point 1/2. This is a zoom into the graph of the third iterate, which we call G. So the point beta is the fixed point under G. Beta prime it's pretty much on the left, so it's symmetric with respect to 1/2. So 0.5 goes to beta prime, under one iterate goes to beta, under the second iterate, and then gets stuck. Now, notice, by the way, that in this case, if you take this interval beta prime beta, which we'll generally call capital I, then both its left side, left half, and the right half are mapped by the third iterate over the whole interval. Now, what happens if you take a slightly larger parameter value? If you take a slightly larger parameter value, then the tip of this parabola will be a little bit below the height beta prime. So what will happen now, you will still have a left interval and the right interval, which are mapped over the whole beta prime beta, but there is now a gap between them. There is a separation. And if you want to look just inside the interval I, if you want to look at points whose orbits stay inside the interval I forever, then what you will see emerging is a picture of a Cantor set. So first, left is mapped over the whole thing, and the right is mapped over the whole thing. For the second iterate, well, there'll be a gap inside the left, which is mapped to this gap, and a gap inside the right, which is mapped to this gap, and so on. And of course, there's a natural symbolic dynamics here. You just use 0 for the left, 1 for the right. Our map G happens to be strictly expanding, both on the left and on the right, in such a way that the invariant set is actually a Cantor set, and the dynamics on this Cantor set with this symbolic dynamics will be the full shift on 0, 1s. Now, in particular, if you take a periodic sequence of 0s and 1s, it will correspond to a unique periodic orbit in this Cantor set. As one example, take the point beta, it corresponds to the sequence of all 1s. Mm-hmm. Let's enumerate all such periodic orbits. There are countably many, so let's enumerate them in some way, call them Pn. And these are periodic orbits of the third iterate, so let's iterate each one of them twice more to capture the whole orbit. And this way we'll get a sequence of periodic orbits of F, which I'll call period sub A of n. So this is a specific sequence.
And let me perhaps point out that these periodic sequences are all repelling, because exactly what you said, the map is expanding on that region. So any orbit nearby will escape from it.
Okay, so now here's the main construction. We denote P, the collection of parameters, such that F sub A has a unique probability measure. And moreover, all of this measure is supported on the set of these repellent orbits, which sounds really strange, right? They're repellent, but the measure will actually be supported on them. And the key theorem is that there exists an uncountable subset of this set, such that for any parameter in this subset, first of all, the measure still, for almost every point, still lives where the measure for the critical point 1/2 is. So, and the second thing is that we can prescribe the values of the weights of the periodic orbits as we like on a dense subset of p hat. So we could put our I mean, you could see that the weights of these orbits sum up to 1, and we could, on a dense subset, we could pick these weights to be arbitrary. Just take any sum that sums up to 1. To illustrate this really quickly, let me show how to put the weights on the orbit of beta. So beta is a repellent periodic point of period 3, but in this example, for almost every point, we'll want to spend almost all the time near beta. And this is how it works. So first, I just want to make a little remark. It's easy to see that to the right of beta, there is an interval j such that the second iterate maps this interval over the whole interval I. So it returns points from here back to the interval I. And now let's look at the following picture. As before, in black is the original map. In blue is the third iterate. This is here is the point beta. This is the interval I. And green is the second interval. This is iterate. This is the interval j. And from in here, this interval j by the second iterate is returned to the middle. So here's what we're going to do. We will overshoot beta prime with the image of the critical point by g just slightly. So we'll go a little bit to the left of beta prime. And then when we go to the right of beta by the next iterate, we'll have to spend a long time near beta, since beta itself is fixed, under the iterates of the blue map. So we'll slowly drift out until we get to the interval j. Now, the interval j is mapped over the whole central interval. So let us select our parameter value in such a way that now we'll return where we started. So we'll return exactly to the point 0.5. So we have this loop for the orbit. Mm-hmm. Well, if you want to see this precisely, here is a more mathematical way to express it. Now, the point is that we are exactly in the situation when the critical point is periodic. So first of all, we have a unique physical measure. It's just supported on the delta masses on the critical orbit. And by construction, since we spend so much time near beta, this measure will be very concentrated near beta. So now let's iterate. Instead of hitting 0.5, let's slightly overshoot it again. So we go into this cycle again and spend even longer time near beta. So here's the picture. Now this orbit returns again near beta, spends an even longer time, and again we'll return it back, and this we can continue indefinitely. And in the limit, we'll obtain we'll obtain as promised a value such that there is a unique physical measure which lives on just 3 points, which are beta and its 2 images. Here's a histogram that you get if you actually try a Monte Carlo simulation for this. You can see the 3 peaks at 3 points.
All right. So, okay. So what this construction gives us, it's the a way of so the physical measure is very sensitive to the parameter, and this is what we are going to use to build our example. So the idea is the following: we just list all the machines that compute some probability measure, and then we pick a parameter in the domain of the first machine, and we ask the machine to compute the measure there at some precision, say epsilon. So after some time, finite time, the machine will halt and give an answer. So since it did it only in finite time, the machine so far knows a finite approximation to the parameter, so say an interval A1. And for any other parameter within this interval, the machine will not be able to tell the difference, so it will halt and give the same answer. And now we use our key theorem to perturb the parameter a little bit, stay within this interval, and change the physical measure by a significant amount in such a way that the output given by the machine is going to be wrong. For any parameter that we pick in this interval, new set given by the key theorem, the machine will halt and output a wrong answer. And now we can iterate this process. So we pick the second machine and choose any parameter in its domain and ask the machine to compute the physical measure at some precision, finer precision than before, say epsilon over 2. And when the machine halts and gives an answer, once again, it knows only a finite approximation of the parameter, and we can play the same game again. Inside a small interval around this parameter, the machine won't be able to tell the difference, and we can use our key theorem to move the physical measure away in such a way that the output that the second machine gave is also going to be wrong. And we can continue iterating this process, and at the end, we obtain a parameter A infinity, say, for which any machine that we try to use to compute the associated physical measure will give a wrong answer. And in this way, for this parameter, we obtain a system having a unique physical measure, which is not going to be computable by any machine, even relative to the parameter.
So that completes the construction. Perhaps just a few open questions to conclude. So in dimension 1, it can be shown that this phenomenon is quite exceptional, and even though there is an uncountable set of parameters, these parameters are very rare. But in dimension 2, the situation when you have infinitely many attractant basins is generic even in polynomial families because of Newhouse phenomenon. So it's very reasonable to ask whether this phenomenon of non-computability could be generic in 2 dimensions.
Another question that we could ask is about the computational complexity. So in order to have, practical intractability, it is enough to face the system for which the computational complexity of its physical measure is high. And this is a weaker notion. So maybe it is also reasonable to ask whether these physical measures could be intractable in higher dimension, maybe with positive probability, for instance, which goes to suggest that such systems may be encountered in nature.
Yeah, it's it's hard to say what this means in practical applications for the Monte Carlo method, but certainly these are very interesting theoretical questions to consider.
Okay, thank you very much.
Thank you.